It's a real pleasure today to introduce Professor Javier del Campo. So I met Javier in Spain, I think it was 2019, at a Biosensors workshop in Alicante, and I was very impressed with the topic, actually exactly the topic that he's going to talk about today. So it's a real pleasure to have you here for the seminar series, and over to you, and looking forward to hearing all about your electrochromic biosensors.
Thank you very much, Michael. Thank you for the invitation. As you said, the talk I'm going to give today builds on the talk that Michael saw already a couple of years ago. So the topic is electrochromic biosensors, and what I want to tell you today is all the process from how the idea originated to the different concept devices that we've been able to produce and to measure. So I hope you enjoyed the talk. And okay, let's see if the PowerPoint will work. Yes. So as you can see, there are lots of points. Hopefully, they won't be very heavy. So first, I will start by introducing my institute, and then my current institute, and then everything else. Because right now, I mean, since November 2019, so it's actually 1 year ago, almost exactly, I changed jobs. I moved from Barcelona, from the National Microelectronics Center, to BCMaterials, which is in the Basque country, near Bilbao. It's right very close to the coast, near Bilbao. So this is a materials science institute. It's a very young institute. It was founded back in 2012, and it is partly owned by the university and by the Basque Science Foundation. So at the moment we are 70 researchers on campus. As you can see, part of our staff, associated staff from the university, and the rest we're all full-time employed in the institute. So this is a summary, if you want to come back later and go through it in more detail, of the activities that we focus on. We have 5 research lines oriented towards 4 areas of application. My line here is the line on micro and nano devices, and this is actually part of my activity over the last year. Also forms part of the contents of this talk. So what we are trying to achieve, I mean, the origin of the idea was we were working on biosensors for point-of-care applications, and this is back in 2015. We were looking at the evolution of these devices. So how communication technologies and microelectronics are shaping the way electrochemical sensors and biosensors are evolving. So you can see that when the glucose biosensor, which is the most successful biosensor to date, started, it appeared as a benchtop instrument with a large instrument and a relatively large consumable. Then back in the 2000s, the technology moved towards screen-printed disposable test strips, and the handheld readers. And then much more recently, what you can find in the market are these sort of wearable systems for continuous monitoring of your blood glucose levels. And so basically what you're seeing is an evolution towards smart systems everywhere, not just in the handheld instrument, in the instrumentation, but also in the actual sensor. So what you can see is that the idea is to move towards less invasive and more comfortable to use, safer devices. But in exchange, what you have is you need to integrate the sensors along some electronics, and at the end of the day, this is disposable. So when you use up this device, you throw this in the bin, and this happens every 2 weeks because the useful life of these sensors are actually 2 weeks. So you're getting rid of not just a wasted biosensor, but also a lot of plastic, electronic components. It's really quite damaging to the environment. It's actually a waste. So what we were looking at is to make something that allowed you to look at your glucose levels, but measuring in sweat. So in this slide, what I'm showing you is how sweat sensors have evolved from around that time, 2015, 2014, up until today. And what you can see is that in these systems, you have all in one piece. So you have the electronics, you have sensors. This is not for glucose, but for sweat electrolytes. This was able to measure sodium concentration in sweat. It has an antenna, an NFC antenna, some control electronics, your ion selective sensor. It's really nice. I mean, all of these works are really impressive. I really like what these groups are doing and all the technology that they are developing, and it's really amazing. So then this other work from 2016, what this is from the Rogers group. They still have some NFC module to power the device, and what this sticker is doing is looking at blood oxygen concentration. So it's really exciting. And then from this year, the same group, they have published a wearable system that that measures your heart rate, and it has a small disposable part and a non-disposable electronics module. So you can see that here, up until recently, the idea was to integrate everything, sensor and electronics, in one piece, and now they are moving back to dividing the electronics and the consumable. I mean, this just makes a lot of sense from the point of view of cost of the device, because at the end of the day, the sensors have a very short lifetime, especially if you want to do chemical sensing. You know that you're going to throw this device in the bin at some point, and that point is coming very, very soon. So you really want to separate the electronics from the disposable. So back then, what we thought was looking from the perspective of systems integration, how people were going about solving this problem. So the way to have wearable devices was to use heterogeneous integration processes, conventional integration and miniaturization from the electronics industry. So you basically make very small components. You have individual functions in individual components, so that the system takes an input. In this case, it would be concentration or whatever analyte information or measurand that you are looking for, and it gives you an output, some information. It can be either a display, or it can be data that is transferred by NFC or by any physical means. So the question was, how can we simplify this? And the way we thought about doing it was to combine functions in the smallest possible number of components. And when you think about it, you realize that a lot of these functions rely on electrochemistry. So, for example, you have obviously electrochemical sensors. Mobile power sources are electrochemical. Lots of them are electrochemical power sources. Batteries, fuel cells. We'll talk about them a little later on. But you can also use other type of materials, for example, electrochromic materials, to have an additional function of information display. So this was the vision back in 2015, to have something like a sticker you could attach to your wrist or to your skin in any case, and have a visible visible indication of what's your concentration of sweat glucose or sweat lactate or whatever. So we wanted to develop a wearable self-powered biosensor. So the goals were to have something that would be affordable, because there's no need to integrate any silicon components. The idea is that anyone can use it and monitor their health non-invasively. But there are some limitations. It must be reliable and safe, so you need to look at the materials that you use. You need to look at how accurate and how reliable the system is as a sensor. We also wanted it to be compatible with mass production methods like large area printing processes. And also, because we know this is going to be disposable, we were concerned with the environmental footprint, both of the processes and of the materials involved in the fabrication. So to minimize the footprint, the first step was to get rid of any silicon components. So this little concept combines many ideas coming from electrochemistry. So the first thing is we wanted to have a self-powered device. So this is going to rely on an electrochemical power source. And when you look at the possibilities, you have batteries and fuel cells. In this case, what we have is a hybrid between a secondary battery. If we make it reversible, it would be a secondary battery, ideally, and a fuel cell. And the reason is that when you look at the construction, we want the system to run on an analyte that is present in the sample. So that would make that would be the fuel cell part. But on the other hand, the amount of electrochromic material on the counter electrode is going to be fixed. So that is why this is almost like a fuel cell, but not quite, and it's not a battery either. So what else? So when you look at how to make a self-powered sensor, the first thing that springs to mind is to use the power generation abilities of the device, and just this is what most people are doing. So you can use the cell potential and the cell power output as indicators of the concentration of your analyte. But in this case, what we wanted to do was to turn the information, the chemical information on the concentration of lactate or glucose in sweat in a progress bar, in something that you could actually see and interpret by sight. So for that, we rely on the internal resistance of the device. So we actually started to use this as a design parameter, and not just as something inconvenient that you want to get rid of. So yes. So how much have self-powered biosensors evolved? The answer is a lot. So the first work was by Katz and Wilner back in 2001. It's a really nice paper in JACS. And what they proposed was a self-powered device. I think their original plan was to use this in implantable devices. Okay, but what they report in their paper is very little power. Okay, they were able to generate measurable differences of potentials that were proportional to the concentration of glucose or lactate, but the power generated was so small that they couldn't power the instrumentation associated with the sensor. So that was more or less the end of it for a while. Okay. Much more recently, okay, this field has evolved because there's been new technology in redox mediators. There's been a lot of new developments on how you immobilize enzymes, how you can use nanomaterials to make this electron transfer more efficient, make sure that you exploit all the enzyme activity. And one of the work where they report a very high power on an enzyme-based fuel cell is this by former colleagues from Barcelona, who are now able to generate powers in the milliwatt range, which is a lot. So you can actually power a small device with this, and it's really nice. Okay, so here I've left you some references if you're interested in these topics. Okay, and this is a map of how the field is evolving. So you can see that the biosensors field is very healthy. You see something like near 6,000 publications every year on Scopus. This is how many papers there are on biosensors this year for 2020. So we'll probably reach 6,000 papers maybe. If you narrow these, and you realize that glucose biosensors are approximately 1/3. So you can see how important this is. And then enzymatic fuel cells and self-powered biosensors are much more smaller topics, much smaller niches. So you get a lot fewer publications. So, but still, it's growing, and it's an exciting field. So there you go. So we wanted to take this self-powered, make a self-powered biosensor, and added the additional functionality of information display. So for this, we turn to electrochromic materials. And then you can see in the literature that you can find self-powered sensors, self-powered electrochromic displays, and also electrochromic sensors. So the thing is, you can combine these three functions in a single electrochemical cell. So for those of you who are not familiar with what electrochromic materials are, basically these are materials that change their optical properties as a function of their oxidation state. Okay, their most conventional applications are in the fabrication of smart windows, smart mirrors. For example, there are maybe some of you have a dimming mirror in the dimming rear view mirror in the car. So that is working thanks to electrochromism. So basically, you use electrochromics for optical devices. But the thing is, you can also apply them in sensing. And here, what I'm showing is a figure that I really like, because it shows exactly what electrochromism is. So you can see how when you change the oxidation potential, the material changes its absorption spectrum. This is for P.PSS. And when you look at the literature, you can see that people classify electrochromic materials based on different properties. If they are organic, inorganic, if they are anodic, cathodic. The classification that I prefer is this one based on the solubility of the materials, or the different based on their oxidation state. And the reason is because we're interested in making a device, and not just a device, but a solid state device. Because when you have a solid state device, it's hopefully more stable. It gives you better control on the material. It responds faster. It gives you it allows for higher resolutions, and it's easier to process as well. So in this case, for the devices that I'm going to show, we focused on these type 3 materials, and particularly Prussian blue. Okay, these are two really nice references that I recommend if you are interested in electrochromism or want to learn more about it. This review by Mortimer is really excellent, and then there's a book, a very comprehensive book on electrochromic materials and devices that is also very nice. So when you look at how to build a sensor based on electrochromic materials, you you can play with different aspects. So the first is the construction, the architecture of the device. You can use the classic sandwich architecture, or you can go for a coplanar one. The difference is that the sandwich architecture normally has a smaller internal resistance, and you get much faster responses. So this would be, for example, interesting if you wanted to make sensors where the information is interpreted from a change in the color or in the tone of the electrochromic material, as in this case. In the coplanar case, what you can do is actually what we do in our device, which is take advantage of the internal resistance and the fact that the current is always going to go through the path of least resistance. So you can actually make a linear color change, as in here. Then you can also classify these devices according to how you power them, and you can have externally powered devices or self-powered devices. And in terms of externally powered devices, you can use anything from a potentiostat to a bipolar system. I mean, what matters is that you can control the potential that you apply between the two electrodes. And then finally, how you read the information. So you can read the information from changes in the color hue, or you can actually create color gradients. So this would be a timeline on self-powered electrochromic biosensors and the relation to self-powered biosensors in general. So here's the first work by Katz and Wilner, and then it took until 2012 for another work to appear, in this case using a self-powered approach, but an electrochromic material. And then from that moment, the field has grown at a moderate pace. I mean, at the moment, I think we can find about 20 papers per year, which is really nothing, describing electrochromic biosensors. And these are some of the milestones. I mean, one very important work appeared in 2014 by Slokziuska et al. They made an ascorbic acid self-powered biosensor, and I think, yeah, this is the reference. So it's a really nice paper. So what was our first concept device? Okay, so now you have all the background, and I've told you where we want to go. So in principle, what we want to do is we want to have a biosensor separated from a display by a permeable barrier. You bring your sample into the biosensor, and this starts everything. So in principle, these two are connected, and as soon as the sample hits the biosensor, you get the system to work, and the display changes color. And the idea is that it will change color as long as the cell potential is able to overcome the internal resistance. So what we have is a system where internal resistance keeps growing, because what I told you a couple of minutes ago about the current going through the path of least resistance, until the cell has not enough power to continue, and then the color front stops. So this was our first prototype, and I'll show you in a minute how we built it and how it works. So the electrochrome that we chose was Prussian blue, which is a material that I really like. It's a material that is not only related to science, but also to fashion and art, and it's actually the precursor of modern photography. So it's really fantastic, and it's biocompatible. So it's very easy to prepare. So it only has advantages. So this is the breakout of our system. So back in 2015-16, we didn't know anything about screen printing, but what we did was to use pressure sensitive adhesive. So adhesive tapes that come from the biomedical industry, because they are used as backing tapes and and to make the disposable strips that you've seen in the glucose meter earlier. And what we did was we cut the protective liner on the tapes, and we put some conducting paste, graphite paste or silver paste, and we just made a stencil out of this so we could print our electrodes. Then we used a lateral flow membrane to facilitate the exchange of solution in the system and be able to reuse it. And then we used an electrodeposited Prussian blue cathode on a piece of glass with an ITO coating. So what we did was actually we used a vinyl mask cut in a cutter plotter to define the area where we wanted to grow the Prussian blue. We ran some electrodeposition using a recipe described by Karyakin, which works really well. And then we basically conditioned the material, because to get the best results, we had to do some electrochemical cycling in HCl, and you can see that the surface of the material improves a lot. It becomes a lot more homogeneous, and actually the response is very, very good. It's quite reversible. So then we started playing with this. I mean, this was the setup. We have some solutions in here that we can change and flow through the system through this lateral flow system. We have an absorbent pad, which is just a paper towel, and this is what we saw. So first we characterized the system by passing constant currents, by polarizing at different potentials, and the image analysis we did using ImageJ. So we could actually compare the position of the color front according to a student that we could grab in the lab. So we could take somebody in the lab and say, well, can you please tell me where would you place the color front here in this picture? And then we compare that with what ImageJ would choose as the point where actually there is a difference in the color. For the biosensor, we used glucose oxidase and TMPD because this was the mediator with the lowest reduction potential that we could find at the time. And then this gave us an idea of what the potential cell at open circuit we could expect, about 400 millivolts, and then hopefully something in the range of 200 millivolts during operation. So this was the system characterization, the polarization curves and the power curves. And as you can see, the open circuit potential was close to what we had estimated from the cyclic voltammograms, but the power was very little. So we were generating something like 10 to 15 microwatts per square centimeter. But the thing is, it didn't matter because all we wanted to was to change the color. So we didn't need to power any additional electronics. So we didn't really care very much about the power. Later you'll see how this is, well, not a mistake, but maybe we were getting the wrong conclusions too early. And when we compare the curves obtained looking at different glucose concentrations, and we compare them with the response of the biosensor, this is normalized, by the way, you can see that there's quite good agreement. So we were very happy about how this thing was working. So the next thing was to model it, to understand what was going on. So we set up some console models of the whole system. So we started modeling the biosensor and the cathode individually, and then we combined both models to see how the system would behave. So these are some of the equations involved. We were we were using Michaelis-Menten kinetics for the biosensor. We were also, because it was very important, taking into account the electrolyte conductivity, because at the end of the day, what we wanted to look at was the effect of the internal resistance, and then some very standard Butler-Volmer electrode kinetics, both at the anode and the cathode. So first we checked the biosensor model. We used the model to extract some parameters from the experimental value, and we saw that, okay, we have something that resembles the experiment. Did the same with the Prussian blue electrode. And here, what I'm showing you in this slide is the importance actually of the IR drop. So in these three cases, what I'm showing is low IR drop or a moderate IR drop. This is cell resistance. And the way we modeled this was by increasing the volume of solution over the surface of the electrode. And you can see that when the medium is very conductive, you get very good potential distribution, and this means that the color is changing more or less homogeneously across the entire surface. So you can see that this is concentration of Prussian blue at the surface of the electrode, but it's equivalent to color. Okay. Then if you make the medium a little more resistive, you start seeing that you get faster changes in this area where the current is coming from. It's coming from the biosensor, so it's coming from the X direction, and this is what you see. And if you make the cell very resistive, you get very sharp drops in the concentration of Prussian blue. So one way to look at this was to do the derivative of this concentration, surface concentration with length, and we got these peak plots, and the peaks are actually an indication of the current density going through the system. So it can also give us an idea when you look at the width of the magnitude of the IR drop. So for example, when there's little IR drop, there is no peak because the change is happening more or less homogeneously everywhere. As you increase the solution resistance, you start getting this peak. It's quite broad, as is the area where you have a color gradient. And then when you make the system more resistive, you get a very sharp color change. We ran the model in galvanostatic and in potentiostatic modes, and what we saw, well, it makes sense, because when you run a constant current experiment, the rate of the process is constant. So you see the same profiles over a distance at different times, because the only thing that's changing is the potential of the electrode. But that's more or less what you expect. When you run a potentiostatic experiment, which is closer to the operation of the self-powered system, what you see is that the shape of the profile is changing depending on the IR drop. So you can see at longer times you have consumed more material, so the internal resistance has increased, and then you have a broader area where there is well, the color front is a little fuzzier. And then what we did was to run the model connecting both systems together and looking at the response. And again, we saw that the system responded quite well at conductivity values in the range of 1 Siemens per meter, which is close to I think 0.1 molar KCl, I think, if I remember correctly. So around here. So what we saw is that if you change the conductivity, you get different responses from your system. You see different current outputs, and you can actually use this also to make a visual conductivity meter, because you can, by just looking at the color of your electrode, if you are in this working range, you can extrapolate the conductivity value. So it's quite interesting. So again, we can use internal resistance as a design parameter. The model, by the way, is available on the journal website as supplementary electronic material. And then after that, the question was whether we could screen print it or not. So this meant changing everything from the materials to the processes, and the only things that remained the same were that we wanted to make a self-powered electrochromic biosensor, and we knew the components that we needed to have. We kept the substrate material, we got rid of glass, we shifted the biosensor towards a redox polymer-based biosensor, and the cathode would still be based on Prussian blue, but it would have to be printable. Same with the electrolyte, and in this case, no paper. We wanted to be able to print everything. So when we started looking at screen printing, you have two possibilities. You can buy a machine, and or if you have one at hand, use it. You'll get more consistent results probably, but it's a much more expensive approach. At the time, we didn't have the possibility to buy one of these machines, so we decided to learn to screen print manually. So we spoke to some really nice guys from the graphic arts sector, and they showed us they taught us how to screen print manually, so we could build a small kit just by buying these two hinges, and well, it's quite straightforward. If you're interested in the process and you want to learn to do this by hand, I recommend this book on silkscreen basics, because it's very nice. It's a very good reference. Then the materials we had to develop were the electrochrom, of course, and the electrolytes. So to formulate the Prussian blue paste, we know that when you screen print, you have layers, or you have coatings that are definitely more than 5 microns thick, typically, usually closer to around 10 microns. So that's a lot. So you need to make sure that the coating is going to be slightly conducting at least. So we looked in the literature, and we found material that is basically silicon dioxide beads covered in a thin antimony tin oxide shell. These are conducting, and then what we did was to grow the Prussian blue on top. So this is how the particles look at the beginning. They are gray, and then as you start growing the Prussian blue on top, you end up with a really deep blue pigment that you can then dry and turn into a paste. So we played with different solvents, different binder materials. We looked at how these would behave on a screen printing process. We checked contact angles, because at the end of the day, well, initially we thought that if it was hydrophilic, it would be best, but then in the end, the Prussian blue is not really in contact with water. So, but you can see that you can play with the composition and achieve different behaviors. And then we did some spectral electrochemistry to characterize the inks. So we have printable Prussian blue, which is very nice, on different types of substrates. So next we wanted to screen print the whole thing. So we went and replicated the same design, same geometry as we had at the beginning. And what we found was that the system was slower, which was not really a surprise, because this, at the end of the day, was about 10 micron thick when the electrodeposited Prussian blue layer was roughly 100 nanometers. So it's a very different material, but it still works. It gives a very nice response, and only the powers are even lower. But this didn't discourage us, and what we did was actually combine it with a glucose biosensor and looked at the behavior, and it was still working. So it was a bit slower, but it worked the same. So the next step, this is the final part of my talk, was can we make this into a wearable? And again, you can see that people are now realizing that they need to get rid of silicon if you want to make a chemical wearable sensor. So in this case, the difficulty was in having the biosensor and the display facing opposite sides. So at the end of the day, what you want is the biosensor to be in touch with the sweat that you're generating, and you want to look at the result just by looking at it. So we thought about how to do this, and also there's a lot of work on the development of this electrolyte hydrogen, but this is actually the fabrication plan. So in terms of the transparent electrode, we could use PSS, which is screen printable, or we could use indium tin oxide electrodes, which you can buy on PET with very high quality. But the problem for us was that if we used ITO, the process was a little more complicated because we had to etch the silicon, the ITO from those areas where we didn't want it. And on the other hand, with the PDOT, we just printed the electrodes, and that was the end of it. So we could streamline the process. Then after screen printing the PDOT, we print the biosensor, the transducer. This is just graphite. The graphite is also used to make the text in the prototype. Then this graphic layer background is a dielectric paste. It's just white in color. Gives you a nice contrast both with the text and with this Prussian blue display. And then we printed the electrolyte on top. After this, we put the adhesive, which can either be screen printed or you can use a pressure sensitive adhesive, which is what we did. And then finally, you modify the working electrode, the transducer, with your biosensor mixture. So this was the plan. PDOT PSS is nice as a transparent electrode, but the problem is that it's also electrochromic. So we needed to be careful because we have to have a material that is a good conductor, but at the same time, it also needs to be transparent, and it mustn't mask the color change of our main electrochromic. So we studied the effect of printing 1, 2, or 3 layers of PDOT PSS. The nice thing is that these layers are extremely thin. They were surprisingly thin. So one layer of PDOT PSS is maybe half a micron or less. So you can print 2 layers and it's still 1 micron, and 3 layers a micron and a half. But it's a very good electrochromic. I mean, that's why it's also used in electrochromic displays, because it doesn't take a lot of voltage, and it turns into a very deep blue color. The problem is that it's cathodic. So we had to see that where these color changes were taking place, and making sure that the PDOT electrode would not mask our main color change, because at the end of the day, we were going from blue to colorless, and here we're going from colorless to blue. So when we combine the two materials, you still get the nice Prussian blue signal and the signal due to PDOT PSS. Here, what I'm showing you are a series of pictures of the typical disk electrode geometry, where we have our PDOT PSS electrode and then we've printed our Prussian blue on top. And what we're doing is we're scanning the potential and looking at the color of the electrode on either side of the device. So you can see when you look from the Prussian blue side, from the solution side, you don't really see the coloration of the P.PSS. But if you're looking from the side of the PET substrate, which is what you will be doing on the wearable device, then it may be a problem. It may be a problem if you work at potentials less than 0 volts. So here, what you can see is the color measured using image J. We take the electrode area and we look at the RGB color, and we are in this case just focusing on the red channel, which is the most sensitive because we want to look at a blue color. Okay, so then when you look at the biosensor that we're using, well, the response is definitely above 0 volts. So this for us is some guarantee that we're not going to go very much, we're not going to go much below 0 volts. So in principle, the system could work. For the electrolyte, we've used an ion gel. So this is an ionic liquid in a PVDF matrix. Printing this was, let's say, interesting because first you need to mix it under a temperature between 40 and 60 degrees. But if you overheat, it becomes yellow. So it looks terrible. And then when you print it, you also have to make sure that it's warm, because otherwise it will clog your screen. So it was a little difficult, but we managed it. Okay. So then what we did with the complete devices, I don't know, I think we're running a bit late maybe, but we're almost there. So we made a lactate biosensor and we connected it to the display. And we look at how the color was changing depending on the concentration of lactate and the time of contact between the biosensor and the sample. And what we found is that we get very sharp, this was unexpected, very sharp color changes. Okay, but the response was actually quite linear. It was even a better linear range than with the amperometric measurement. And I think this is because once you have a given concentration of your analyte, you establish a potential difference. And that is what determines how much color you are going to change. And because we're leaving it so long, the color just becomes very sharp. So it's actually a nice way to do colorimetry. So you see how we've gone from this vision in 2015 to these devices in 2020. And this is actually a prototype artwork. This is the hand of a student back from the University Autonomous of Barcelona. She went for a walk, and 30 minutes later, she could see that actually the biosensor was changing. It was actually working. So not bad. We were very, very happy. So as a summary of the conclusions, well, if you want to have multifunctional components in a device, you need to involve multi-responsive materials. In this case, electrochromic materials are redox materials with a color change as a function of oxidation potential. Then these electrochromic materials are very nice because they allow you to build self-indicator components. So you can have self-indicator batteries or self-indicator sensors, as in this case. Internal resistance may be a bad thing in traditional electroanalytical chemistry, but in this case, you can actually use it to make a nice working device. And then what you definitely need is that the architecture, the materials involved, and the processes you use to make your devices are in harmony. So every change in architecture may have an impact on the materials or the processes and vice versa. And then to improve the performance the device that I've just presented you, you can actually improve the biosensor, and this will improve the response time. You can also changing the biosensor to increase the cell potential, or changing the electrochrom to get wider or narrower dynamic range for your system. And you can maybe access other applications if you change the transparent electrode and use more inert materials. So, this is it. I mean, here I would like to thank everybody who has been involved or who has supported the project, starting with the staff at the CNM, where all this began, and the biomedical applications group where I belonged, and then our collaborators in the university, the group of Gonzalo Virado, who developed the ion gels, the group of Yaniv In and Boris Lacard in UTINAM, who helped us a lot by providing us with excellent students. And here at BCMaterials, Diego Rio, who performed some of the experiments that you've seen in the latest part of the talk, and Senen Chulanceros, who's the director, and who has given me the opportunity to be here talking to you today. And then different people from industry who have helped hugely with knowledge or with materials, and you know, they've been really supportive. And finally, funding sources, BBVA Foundation and the Generalitat de Catalunya, and finally Iker Basque. And this is it from my part. If you would like to ask any questions, I'll be very happy to answer them.
Thanks, Javier. It's a brilliant talk, moving all the way from initial concept to TRL level 4 or 5. So it's actually quite inspiring from that point of view. It's really nice to see it leaving the lab and walking down the road in someone's hand. So it's good. Yeah, so if you could stop sharing and the screen, and I'll